I want you to close your eyes and try to picture absolutely nothing. Not a dark room and not the empty space between stars. An absolute, total void. No time, no dimensions, and no light to cast a shadow. It is a concept the human brain isn't wired to process. Yet the smartest people in the room, using our most advanced math, believe that every single thing in our reality, from the device you're watching to the Andromeda Galaxy, burst out of that state of absolute zero. It's the ultimate free lunch. To figure out how you get a universe from non-existence, we have to bridge two radically different scales. We have to take cosmology, the study of the largest event in history, and smash it into particle physics, the study of the tiniest objects ever recorded. 13.8 billion years ago, the entire universe was squeezed into a space smaller than a subatomic particle. At that scale, the rules of the tiny governed everything. To understand the explosion, we have to look closely at the shrapnel it left behind. Let's open the pantry and look at the actual ingredients of the universe. What we experience as solid matter is mostly empty space. Even the protons and neutrons inside an atom aren't solid marbles. They are bags containing even smaller, more fundamental building blocks called fermions, specifically a type of fermion with a whimsical name, quarks. You will never find a quark alone. They are bound together by the strong nuclear force. If you try to pull two quarks apart, it is like stretching a rubber band. When the band snaps, the raw energy immediately turns into mass, creating a new pair of quarks. Matter refuses isolation. Alongside quarks are leptons, including the ghostly neutrino, which ignores almost everything in its path. Trillions of them from the sun are streaming through your body right now, as if you were just a vacuum. You have a pile of these subatomic bricks, but they won't build reality without mortar. That is where the bosons come in. They are the force carriers. When two magnets repel each other, they are literally throwing streams of messenger particles at each other to communicate the force. Reality is a dynamic framework of interacting particles and forces. If you remove all of them to create a perfect void, you uncover the mechanism that started the universe. In modern physics, nothing is almost never empty. A pure quantum vacuum is a restless, seething cauldron of activity. This stems from the Heisenberg uncertainty principle. One version of this mathematical law dictates that for incredibly short fractions of a second, the energy level of empty space can fluctuate wildly. Empty space can borrow energy from the future to create mass, popping a virtual particle and its antiparticle twin into existence out of thin air. Nature allows this million-dollar loan, provided the two particles instantly crash back together, annihilate each other, and return the balance to zero. This is happening everywhere, constantly. But if this cosmic debt is always instantly repaid with mutual destruction, how did we get a permanent universe? To get a universe that lasts, you need a physical mechanism capable of ripping those borrowed particles apart so fast that they lose track of each other before they have the chance to cancel each other out. The Big Bang represents the sudden, spontaneous expansion of space itself from a single point of infinite density. A tiny fraction of a second after time zero, the universe underwent cosmic inflation. Space itself stretched outward faster than the speed of light. Einstein proved that nothing can travel through space faster than light, but space itself can expand at any speed it wants. This hyper-expansion solved the quantum loan problem. The virtual particles bubbling in the vacuum were violently ripped to opposite sides of reality. With their partners gone, they couldn't annihilate. The loan was forgiven, and those temporary particles were locked into permanent existence. Following this burst, the universe was a chaotic plasma of loose quarks. As space expanded, it cooled in a process called symmetry breaking. The intense energy dropped just enough for the strong nuclear force to finally clamp down, snapping those quarks together into the universe's first protons. Inflation allowed the universe to take a temporary microscopic quantum fluctuation and freeze it in place, generating the permanent reality we inhabit today. For the first 380,000 years, the universe was a searingly hot, completely opaque fog. Free-roaming electrons were buzzing around with so much energy that light could not travel more than a tiny distance without violently scattering off of them. Then, the universe reached a critical threshold. It cooled to about 3,000 degrees Kelvin, which was just cold enough for protons to pull those chaotic electrons into stable orbits. The first neutral atoms formed, the fog lifted, and light finally traveled freely. In 1965, two scientists testing a radio antenna in New Jersey picked up a persistent hiss. Blaming nesting pigeons, they scrubbed the machine, but the hiss remained. They had accidentally recorded the cosmic microwave background, ancient light matching the Big Bang, showing microscopic seeds of galaxies. This background radiation is the literal, observable echo of the universe's creation, and it is still raining down on Earth right now. Everything we've tracked so far, the quarks, the atoms, the gas clouds, and the stars, makes up a grand total of 5% of the universe. The other 95% belongs to the dark sector. We have dark matter, the invisible glue holding galaxies together, and dark energy, the mysterious force causing the expansion of the universe to accelerate. Our 5% of normal matter was lucky. The early universe produced almost equal amounts of matter and antimatter, which should have completely wiped each other out. But there was a tiny imbalance, just one extra particle of matter for every billion pairs of antimatter. We are the survivors of that great annihilation. Mapping these origins requires a colossal infrastructure, machines the size of cities that generate petabytes of raw information. In 1989, researchers at CERN realized that sharing these massive datasets with thousands of scientists across the globe was physically impossible through traditional means. To solve this, Tim Berners-Lee developed the protocol that became the World Wide Web. Our entire information age is a byproduct of hunting for quarks. The Big Bang exists as a continuous state of being. The quantum mechanism that ignited the universe remains active in the empty air right in front of your face.